Hi guys, next we will talk about the differentiations of the functions by using the properties of the Laplace transform. So as you can see in the slide here, I have the time differentiations property, and you can see that we have when you have to find the functions or the solutions to that of the first order differentiations or even the second order differentiations, we can also apply the Laplace transform method on that functions and then get the solutions, right? So here in this case, for example, let me give you the starting point. Right, so if you have the Laplace transforms of the functions ft divided by dt, so it functions in the s domains or in the frequency domains will be equal to the s multiplied with the big of s minus with the small f of 0. Or if you want to find the Laplace transform of the second order of that ft and then divided by dt squared, that will be the s squared multiplied with the fs and then minus with the s raised to the power of 1 multiplied with the f naught and then minus with the f plums are not. And also if you have like the differentiations of the third order of that ft divided by d raised to the power of 3, that will be equivalent to the s cubed multiplied with the big F minus with the s squared multiplied with the f naught minus with the s and also multiplied with the f plums naught and minus with the f double plums naught, and so on until when you have the Laplace transforms of the d raised to any nth order of that ft divided by dt raised to the power of n. So you will have the s raised to the power of n multiplied with the s minus s raised to the power of n minus 1 f naught and then minus until you have the f raised to the power of n minus 1 naught. So here is the properties of the differentiations of the functions, right? So for example, let's say the example one for that differentiations, when you are asked to find the Laplace transforms of the second order differential equations, which is y double prime t plus 3y prime 3 plus with 2yt equivalent to ut. So our goal in these kinds of questions is that you first have to transform the times domains into the S domain first, and then when you got the S domains, you will have to rearrange that S domains in terms of the solutions of the YS, and then from that YS, you will have to use the inverse Laplace transform to get the times domains of that yt. So in the first step here, we apply the Laplace transform. So that is the step of applying the differentiations onto that functions. For example, this case here, you have the Laplace transforms of y double prime t adding up with 3y prime 3 plus 2yt equivalent to the ut. So if you could remember this ut here, ut actually is mean the unit step functions. So when you have these kinds of graph here, and then you have the unit step function, let's say the amplitude is 1, and that's it, the graph here. So if you have the unit step functions, means that from the times greater than or equivalent to 0, your amplitude here will be equivalent to 1. So this is the unit step functions. So the unit step function in time domains here, when you apply the Laplace transforms, it's S domains or its frequency domains will be equivalent to 1 divided by the value of the S. But also remember, if you have if you have the lamp functions, okay, let's say these ones, if you have the lamp function here or an increasing here, okay, so if you have these kinds of functions, it's called the lamp functions. So which means that your ft equivalent to the value of t, and then when you apply the Laplace transform onto that lamp functions, increasing functions, so your s domains or your functions in the frequency domains, the fs will be equivalent to 1 divided by the s squared. So that's it, the difference between the unit step functions and the increasing or the lamp functions here, right? So let's go back to our case. So if you can compare here, you have the y double prime 3. So y double prime 3, so you have to apply this property. So this property here is for the second order. So you will have the Laplace transforms of the y double prime 3 adding up with the Laplace transforms of 3 multiplied with y prime 3, adding up with the Laplace transforms of 2y3 here, and that's equivalent to 1 divided by s. So we already changed, or we already transformed the ut into the s domain, which is equivalent to 1 divided by s, right? So next, we have to solve for this, and this in terms of the s domain first. So let's start with the second order here. So when you have the y double primes, and that will be equivalent to the s squared. So here you have the big F. So now you will change into the big Y, because you are given with the y term, but in this case you are given with the f term, so you have to have the big F terms here, and then you will have the minus sign with the s, and then you have the y naught here, right? So you are done with the second terms, and then the last term would be changed from f primes into the y prime naught minus with the y prime naught. All right, that's for the first ones. And the next one, so next you have the additions of these three, right? You have the additions of these three. So number 3 can be written at the front of the Laplace transforms of the y prime 3. Okay, and then you have additions of 2 multiplied with the Laplace transforms of the y t. Okay, so now what we have to look at is this case, the Laplace transform of the first order, which is the first one here. So let me draw the box for you. So that's it, the property we have to apply all the times when you are given with these kinds of the ordinary differential equations. So when you have the y primes, right, so that will be equivalent to, in this case, that will be equivalent to 3 multiplied with the s y of the s minus y naught. That's it. And then in this case will be 2 multiplied with the from yt here, you will change into the y of s. Therefore, you will have the s squared ys minus s y naught minus y prime naught here, and then you have the additionals of 3 multiplied with the s ys minus with the y naught plus 2 ys here equivalent to 1 divided by s. So basically you find the Laplace transform for each of the terms, and then you apply that, right? And our next step here, so suppose you got that explanations. So our goal is to find the ys first, like I told you at the beginnings, and then you will have the conditions for ys equivalent to some functions, and that will be given in terms of the relational functions. Okay, and then after you got the solution here, you will have to apply the partial fractions, the partial fraction method, right? Okay, you have to apply the partial fraction method after you got the relational functions. So that is the concept or the differentiations of the functions. So basically you just apply the concept of the differentiations property back into your ordinary differential equations, and then you solve it out. So let's take a look at the example here. So example number 2, suppose you are asked to solve y double prime t plus 3y prime 3 plus 2yt equal to 0, and then you are given with two different initial conditions. So you got y0 equal to 1 and y prime not equal to 2. So now you have to change from that ordinary differential equations into the S domain first by applying this function here, right? So you have to find the Laplace transform for the y double prime t. Basically, you have to find for every terms, right? The constant here can bring it at the front, so you will have this one. So the Laplace transform of the 0 becomes 0. So the first one, you have y double prime t, so that becomes s squared ys minus with the s y naught and minus with the s prime 0, right? That's for the first one, done. And then the second one, you have the additional of 3. So the Laplace transform of the first differential is the sys minus with the y naught, right? If you can compare that to this one, that will be that. And then addition with 2, so you have to find the Laplace transform of the yt. Basically is equivalent to the y of s, and that's equivalent to 0. So okay, so now after that you will got the everything in terms of the S domains. So here in this case, as you can see that we can now apply the IC, the initial conditions, okay, back into that expression. So we got the y prime 0, which is equivalent to 2, and we got the y naught here, which is equivalent to the value of 1, right? And then you rearrange the expression. Therefore, after you arrange the expressions here, right, so that's 1 as well. So that is the y naught, which is equivalent to 1. Okay, so now we want to find the ys, which means that we will move the other terms apart from the ys onto another side, and we left ys on the one side of the expression. So here we will have the s squared ys minus with the s multiplied with 1 minus 2. So that is for the first expressions, and adding up with 3 multiplied with the ys, right? And then minus with 3 multiplied with the minus 1, so that becomes the minus 3, and then you have the additions of 2 multiplied with the ys, make that equivalent to 0 according to the questions. And now we will group the same. So these ones that become s squared, and then you have the ys. So next is you have to look for the group of the ys. So that is the first ones, that is another second ones. So you will have that, right, for the ys, add with 2 multiply with the ys term here, and then the remaining terms are these 2 and that 1, right? So you will have minus s, and then minus 2 minus 3 equal to 0. So again, in this case, you can see that this ys, and this ys. So we can make ys at the front, and then inside the parentheses, you will have the s squared plus the 3s, and then plus 2, right? And minus with s, so minus 2 minus with 3, so that becomes the minus 5. So makes that equivalent to 0 first. So now After that, we will move these two terms on the right side of the equations. So therefore, on the left side, we will have the ys multiplied with these terms. So that become s plus 5. Okay, so remember, our goal after applying the differentiation property here, we have to look for the ys. That is our goal. Right, this case we have to find for the ys, but that ys will be given to you in terms of the relational functions, and after that you have to apply the partial function method. Right, so you have the s plus 5 divided by that. Okay, s squared plus 3s plus 2. So now we got the ys. Right, so in this case, you have to first consider whether that equations or that ys is the proper or is an improper functions. And if you know that is it the proper or improper, you have to continue finding the further step. So let's take a look at that together. So in this case, as you can see, the degree for that is 1 and the maximum degree for the denominator is 2. So this is the proper functions. So if that is the proper functions, you can use the partial fraction method to find the terms. So therefore, our ys here will be equivalent to s plus 5 divided by, if we take a look here, we likely to get s plus 2 multiplied with the s plus 1. And again, in this case, the maximum degree is 2, which means that you need to variable in this case. So let me name it as the a divided by s plus 2, adding up with b divided by the s plus 1. So now you got two expressions, and then we will find the solution to a and b, right? And then we'll use the inverse transform back. So that is the first step, right? And the second step, you will have to multiply the s plus 2, s plus 1 on the both sides of the expressions. So therefore, on the both sides, just only that, we will have the s plus 5 divided by the s plus 2 multiply s plus 1, and that also need to multiply these two terms, right? Done for the left side, and then for the right side, we will have that for the a and that for the b. And again, these two terms we have to multiply by s plus 2 and s plus 1. Right? So this and this and s plus 2 can be eliminated at s plus 1, and thus s plus 1 can be eliminated out. So therefore, on the left side of the equations, we have the s plus 5 equal to a multiplied with the s plus 1 plus b multiplied with the s plus 2 left. Right, and then you cross multiply here, you cross multiply here, so you have the as plus a plus the bs plus 2b, right, equivalent to the s plus 5. So third step, you have to group the same coordinates. So the maximum degree is the s, so you have to look on both sides of the expressions for the constants or for the variable that contain the s raised to the power of 1. So we have that for the first group. And then the remaining terms here will be for the constants. So you make that at the 5 equal to a plus 2b. So this s, and this s cancel out. Therefore, you have 1 left equal to a plus b. Therefore, our a is equal to 1 minus b, right? And then next, you have to substitute a as 1 minus b back into the second group, and here is what you will have. So you will move 1 to the left side, so that becomes 5 minus 1, and that becomes minus b plus with 2b. So you got that's minus 1 plus 2, that becomes the value of the value of b. So therefore your value of b is equivalent to 4, and then you substitute that into the value of a. Therefore over a here is equivalent to 1 minus 4, which is equivalent to minus 3, right? So now you go back to your first step, right? After you go back to your first step here, you can see that you have the y of s equivalent to a, which is equivalent to which is equivalent to minus 3 divided by s plus 2 plus b, where your b here in this case is the value of 4 divided by s plus 1, right? And then next step, you have to find the inverse transform, right? You have to find the inverse transforms of the value of that functions fs, right? So you have to find the yt in this case, okay? So yt in this case here, remember that you can apply the, if you could remember, when we have the ft equivalent to the exponential functions of the at, so your big fs or the s domains by applying the Laplace transform will be equivalent to 1 divided by s minus a. So that is the exponential that is going toward the right side of the graph. So that's it, the curve. So the other way around, if you have the ft equivalent to e raised to the power of minus at, so your your fs will be equivalent to 1 divided by s plus a, because your graph here is going toward the left side, okay, the left side here of the graph. Therefore that's it, the property of the exponential functions. So if you compare that, you will have something similar to the exponential functions, okay? You have something similar to the exponential functions. So therefore, after you transform that, minus 3 at the constants remain the same. So you have to find the Laplace transform of 1 divided by s plus 2. So s plus 2 here is similar to that exponential functions. Therefore your terms domains will be equivalent to the exponentials of minus 2t, right? And then 4 here remain the same, and next is 1 divided by s plus 1. So again that's the same property. So you will have the 4 multiplied with the exponential of minus 1t, okay? So this is the final solutions of the inverse Laplace transform when you are given with the ordinary differential equations, and also along with the initial condition. You can see that this is the step. So we first transform, okay? So we first transform the differential equations into the s domain first, That's it, our second step. And from the s domain, you have to rearrange the expressions here to get the rational functions for the ys. So you will have ys equivalent to some a divided by b functions, which is called the rational functions. That's it, step number 3. And after that, you can see that we can consider the ys into 3 different cases, whether they have the distinct roots, they have the repeated roots, or they have the conjugate or complex roots. And then you apply that rational functions, find its roots, and then you continue finding the 4th step with it to find the yt of the inverse Laplace transform of that partial fractions expansion. So this is the 4th step, okay, of determining the differentials of the functions for this kind of question, right? So that is the solving linear ordinary differential equation by using the Laplace transform. Thank you.